So our goal today is to prove the mean value theorem, which I'll introduce you to in just a little bit. It has a nice intuitive result as well as a nice calculus-related result. So I think we'll get an appreciation for that over this unit, over this section. But before we can do the mean value theorem, we need something called Rolle's theorem. Okay? So we've actually sort of been building up for this. We had Fermat's theorem from the last unit, or from the last section, and then we've got Rolle's theorem now, and then we'll jump into the mean value theorem. So Rolle's theorem says this, and this is start paying attention to these conditions that are required on these functions. It says let f be continuous on a closed bounded interval, and differentiable on the interior of that closed bounded interval, on the inside of it. And this is kind of a strong assumption, we don't often see this. What does that say? I mean, I know it says f of a equals f of b, but so you translate that for me. Not necessarily. That's true. That's true. So, I'm sorry. Yes, it is not a one-to-one function. That's true. That's true. We can say a little bit more. You said?
Is it that the endpoints are equal?
Yeah. So the endpoints of this function are equal. That's what we're requiring here, which is a kind of a strange assumption to make. So we're requiring that the left endpoint and the right endpoint are the same here. If that's the case, then there exists a C in the open interval a to b, so that f prime of c equals 0. So here I say that Rolle's theorem connects two intuitive notions regarding continuity and horizontal tangent lines. Suppose an object begins and ends at the same spot, like a ball thrown up into the air. Right? It starts and ends at the same height. Then as long as the motion is well behaved, what do we mean by well behaved? Well, mathematically we say as long as the motion is continuous, then there's guaranteed to be a point in the interior where the derivative is 0. And if you go back to that example of the ball going up and coming back down, there was a point where the derivative was 0. Okay? That's not unique to that one physical phenomenon. Okay? So let's try and convince ourselves that this is true. Okay? So connect these 2 points. Here's the order pair a comma f of a. Here's the order pair b comma f of b, and just try to find a way to connect between the two. Now, there are 2 conditions. You can't have any cusps, corners, or vertical tangent lines, because we said it had to be differentiable on the interior. And it has to be continuous.
Did it say at least one or only one?
It said at least one.
Okay.
Yep. So careful with those existence proofs. We don't usually say the phrase at least one.
Right.
But often when we say there exists something, it doesn't preclude there existing more than one.
Okay.
Yep. Yeah. Great. Yeah, that's a really good point. Because for instance, if we connected the line like this, then notice we found 2 C values. Maybe we call this one C1. We call this one C2. And that's where we have horizontal tangent lines. So you fill out the other 2. Rolle's theorem says there's no way you can get from point A to point B in a continuous manner, differentiable on the interior, without having a place where you have a horizontal tangent line. At least one. Yes?
You'd also have an infinite amount of C's if it was just a line. Right?
Good. I like that. So let's do that. Okay. So let's look at that case. I'll put that one over here. Good. Keep that case in mind because we're going to need that as we're proving it. Right? So if you've got a constant, then of course everywhere you have is a horizontal tangent line. That's true. Yeah. And then maybe as a third example, I don't know, maybe we'll go down like this. And then sure enough, yep, here at this C value right here, we had a horizontal tangent line. Okay? All right. So let's prove Rolle's theorem. And actually the proof of Rolle's theorem is going to examine, we only drew 2 of the cases on the board, but we'll consider two cases. Okay? So case 1, let's examine the case if f of x is constant on AB. then what's the derivative of a constant? F prime of c is necessarily 0, or excuse me, that will be true, but because f of x is a constant function, that means f prime of x is 0. Okay. So, for any c in the interior, just because the function's derivative is identically 0, then so is the derivative at any point. That's not really an exciting example, but it's going to actually allow us to break this up into 2 additional cases. Okay? So if it's not constant, then at some point it either has to rise or it has to fall. Right? So you can either be constant, meaning not changing, or at some point you have to increase, or at some point you have to decrease. Now you might increase and then decrease, or decrease then increase, but you have to at some point do one of the 2.